Alrighty. Welcome to episode 5 of the exercise application assignment. I'm your host, Graylin Moon, resident suck up or whatever. Comedy's not my strong suit. Okay, so today let's cover training right quick. So training today was pretty much, today it was chest and biceps, and a little bit of shoulders. So slightly restructured. I had it as chest, calves, and biceps, but I decided to switch it out for shoulders because it's a bit more traditional, I reckon. But I mainly did it just because I wanted to spread out my calf stimulus, if that makes sense. But basically the workout was incline chest press machine, the converging one, and then weighted dips. Then what did we do after that? I say we. What did I do after that? Let me grab a book. I'm fairly certain it was uprights, yep, with partials, and then preacher curl machine, then 45-degree dumbbell forearm curls, which is like you get on the preacher curl thing, you're holding your arm at 45 degrees, you're curling a dumbbell like that, opening your hand at the bottom. I like to go really heavy on that. Then reverse curls and hanging leg raises. So yeah, pretty much really focused on the front of the body, for that day in particular, or this day in particular. Doing little things like when I do my weighted dips, it's kind of a drop set. I just do the weighted dips and then I burn out on body weight immediately after. So that's what I did. Now let's talk about how that relates to what we covered in lecture today. So lecture today was over kind of the first sort of part of chapter 7. So that's what I'll talk about. So we basically covered nerve impulses and how they start moving stuff around. So basically, you have the nerve cell. You've got dendrites and an axon. It looks just like this. It looks just like my forearm, actually. These are your dendrites, axon, okay? And we receive the signal, right? Let's start with this. So in the cell, this is your soma. The palm is my soma. We have these fixed anions, which is kind of like all your structures in there, like your organelles and whatnot, and some other things that are negatively charged in general, and they're fixed. They don't really go anywhere. And then you have a high concentration of potassium inside the cell, and then a high concentration of sodium outside the cell, and vice versa. Like low sodium, high sodium, low potassium, high potassium, right? So you can kind of see you have a concentration gradient going here. And basically, if we're starting at a certain point, sodium's going to influx into the cell. Like we're going to receive, a stimulus that'll get some of these sodium channels to open. Now, if not enough of them open, nothing happens. But, if enough sodium gets in here and we get up to threshold, which is negative 55 millivolts, we're starting out here at negative 70. If enough sodium comes into the point where we're at negative 55, then it's like, oh shit, oops, I cussed. But then all the sodium is like, well, we're just going to be crashing in. We're all going to crash in. And so what I like to imagine happens is you get like a little signal on this dendrite, and it reaches threshold. And as soon as it reaches threshold, it's like, and all the gates like go around like that. That's what I imagine. Hopefully that's right. And then it starts propagating down the axon. And then, as soon as that happens, the sodium pours in, Then the potassium channels open, and we kick potassium out because we've got to repolarize. So it's like this huge, like, bing, this huge spike of like a domino effect going around the outside membrane of the cell, and that's when all the sodium comes in. The same thing happens to the potassium going out. So it's like whoosh, sodium in, whoosh, potassium out, and that's happening. That propagates all throughout the cell, and then it hits the axon. And then when it hits the axon, it's either myelinated or unmyelinated. Same difference. It basically just means if the propagation is going to go like whoop, or if it's going to go boop, 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 So that's the deal there. And, then we're in this sort of refractory period after that where we got to return to baseline. So if we just kicked all our potassium out, but in order to start, we need to have a high concentration of potassium in the cell, our sodium-potassium pump is going to use ATP to exchange 2 potassium and 3 sodium. So inside the cell, we got 3 sodium, then ATP will come and kick that out of the cell, bind the phosphate group to the pump, and then we'll grab some potassium, and then as soon as that happens, it kicks back, phosphate group falls off, potassium comes in. So that's how we kind of return back to the baseline, the resting membrane potential of negative 70 millivolts after the fact. And that's what's known as your refractory period. So that's pretty much all we covered in lecture. I mean, there's also the neuromuscular junction and how that's transferred. So you get your action potential, it comes down, we get to the little synaptic input, which I guess in this case will be my elbow. This is the input right here. And inside the input, we have these synaptic vesicles that are carrying acetylcholine mainly, or I think in some cases it can be norepinephrine, or something like that. Yes, I believe so. Either way, it's going to have either an excitatory or inhibitory neurotransmitter in it, these little vesicles. And I've just used acetylcholine, for example, because I think it's the most common. Basically, that action potential gets sent down, and then it stimulates these synaptic vesicles to release, and they get basically ejected from the input, and they bind to these ligand-gated protein channels on the postsynaptic, what's it called? The postsynaptic membrane. So there's this gap called the synaptic cleft, and they go across and they bind to these ligand-gated little channels. And when they bind, they're sodium channels. They're ligand-gated, so that means that acetylcholine or whatever is binding to it, right? I think a ligand is a term. I forget what ligand means, but I just think of it as special chemical key. That's what I think of. So it binds to it. Like you got acetylcholine, boop, boop, and then it opens up, and then the sodium comes flooding in through, the gates, right? So if not enough gates open, that's not going to happen. And then I won't cover the stuff that we didn't cover, but that's basically what we got to. And then, of course, you got to clean that up afterwards. So this enzyme called acetylcholine esterase, Pac-Mans, all the acetylcholine up. How does that apply to my training? Well, you gotta move. So the neuromuscular junction and all that is vital for moving. So the end part that I just described there, where we have a signal that's transmitted into a cell, that also works. That works from neuron to neuron, but it also works from neuron to muscle tissue. So I did bicep curls. That's the example we used in class. I did the preacher curl machine. I'm sending a signal from my what is it? It's whatever nerve into my bicep, and then that nerve gets to the end, and then the input shoots out the acetylcholine, opens up the ligand-gated channels, and then then we have muscle contraction, right? And it's stimulating my muscle to contract, and that's a good muscle to contract. But that's basically what we covered. So Interesting thing I read was that, in the book at least, in strength sports. Oh wait, did we? I'm not actually no. I'm not going to cover that because that's way down. That's way in the chapter. I'll save that for the next episode, Dr. Dre. But that'll do it for today. I think I made a decent connection there. I don't know. I mean, it's pretty simple. I mean, if your muscles are gonna move, you gotta have your nerves tell them what to do. So that'll do it. I'll see you in the next episode.